to okay, I was interrupted. I'm looking forward to meet you all at Combura, for instance, or maybe any other conference organized soon, I hope, because, well, I can't see you even, and talking to my screen is getting a bit boring, but I try to keep you awake and prevent you from an after lunch dip. What am I going to talk about in the next 45, well, maybe an hour, is about hydrogen flames, hydrogen combustion. And I'm not going to talk about why we should burn hydrogen or how to do that. That's not the topic of this presentation. The topic of this presentation is why hydrogen flames burn differently. So it's maybe a bit more scientifically oriented than the next presentations in this series on hydrogen combustion within the Dutch section of the Combustion Institute webinars. Okay, so I'm going to talk a lot about preferential diffusion and the dynamics of hydrogen flames or blends of methane hydrogen, because that's also relevant. Pure hydrogen is nice, but blends are also interesting. So if you don't know what preferential diffusion is, don't worry, I'm going to explain that to you. Well, let's see where this presentation brings us. Now, how to get to the next slide. Oh my God. Yeah. So I told you I'm not going to talk about why we burn hydrogen, because that's already explained by the famous Dutch scientist, Frans Timmermans. His quote is down there on the slide, saying, let me see if I can use the laser pointer, yeah, that we need to decarbonize and going towards climate neutrality, nice words, and importance of hydrogen seems to increase on a daily basis. And even last week, the Dutch government announced their plans during Prinsjesdag, last Tuesday. You must have heard it if you live in the Netherlands. And in these plans, they have reserved quite a lot of money for hydrogen. There's 750 million euro investment in the hydrogen backbone so that we can build a big gas grid suitable for hydrogen, and lots of other money for electrolysis and for hydrogen storage in salt caverns. So it's picking up speed. And of course, I don't have to explain you that this hydrogen receives a lot of attention, because if you burn hydrogen, you don't emit carbon dioxide. Of course, if you make it, you may produce carbon dioxide, so I have to consider that. But it's probably the easiest fuel to produce from renewable electricity, and therefore it's considered to be a good way to store energy. Yeah, so renewable electricity, when the sun shines during the day, we hardly need electricity, so we can convert that into hydrogen and then use that for energy storage. And hydrogen then has a huge potential. The use of hydrogen, of course, for industrial heat, high temperature processes, but even for residential heat where electrification is somewhat harder. Power generation and the transport sector, of course, planes, trains, automobiles, maybe. All of those could benefit from the use of hydrogen. So that's why we might do hydrogen combustion. But that was not the main topic. My buttons do not work. So, okay. This works. Hydrogen fuel. So using hydrogen as a fuel or as a partial replacement for fossil fuels, think about natural gas or methane, is a good idea, because then you can reduce the CO2 emissions per unit of energy. However, burning hydrogen is not that straightforward, because current existing combustion equipment might not be suitable. You cannot just simply replace that. Like a diesel engine, you cannot just pour in gasoline, and the same holds for a device that's designed to burn natural gas. You cannot simply replace it with hydrogen. I guess you all know that. Some basic properties of methane and hydrogen as fuels are listed over here. Of course, their energy content, which is way different. Hydrogen on a mass basis has a much higher energy content. However, it's also much less dense. Density is much lower than methane. So on a volumetric basis, the heating value of hydrogen is actually lower than that of methane. 3 times as much. However, you also need you need much more air for methane than for hydrogen combustion. And actually, if you compute the energy content of a stoichiometric mixture, then it's about the same for both on a volumetric basis. So the same cubic meter of fuel air contains about the same energy. However, the ratios of fuel and air are completely different. So if you, you can imagine that combustion equipment needs to be modified for that. Other important differences are the flame temperature. Hydrogen is typically a higher flame temperature. So the adiabatic flame temperature at stoichiometric conditions is about 150 K higher than that of methane. The biggest difference maybe is the burning velocity. Hydrogen is much more reactive, has a much higher flame speed at stoichiometric conditions. You know, it's about 6 times higher, and at richer conditions, it can burn even faster, which is also an interesting thing by itself. Much higher flame speeds, which of course is relevant for stabilization, which we will see later. Flammability limits are much wider, so very lean and very rich mixtures can burn. Autoignition temperature is not that much different, but the amount of energy needed to ignite a mixture of hydrogen is much less than that of methane. So you can ignite it much easier. A little spark can already trigger a combustion process, an explosion maybe. So for safety reasons, this is an important property. Another thing which is very important in this presentation is the diffusivity, the mass diffusion of the fuel in the air. And this is at standard conditions. For methane, it's about 0.2 square centimeters per second. And for hydrogen, it's about 3 times, almost 4 times higher. So it has a much higher diffusivity. And that results in much lower Lewis number, which gives rise to all these interesting phenomena. So I'll keep struggling with this. Yes. The flame properties, I mentioned already temperature and flame speed, and these are the main properties for premixed combustion, because these properties depend on the fuel equivalence ratio, the ratio between fuel and air. Highest temperatures near stoichiometric conditions and about 150 K higher for hydrogen, pure hydrogen. But that's good. High temperatures means high heat transfer. That's nice for some processes, but of course, high temperatures also cause high NOx formation rates, and that's not nice because we don't want NOx emissions. The flame speed is also vastly different, as I already said. And here you see the measurements and modeling results for the laminar burning speed of hydrogen, methane, and a mixture of hydrogen and methane. And what we see is that we can burn hydrogen much faster. And that's nice because if it burns fast, you can produce a lot of power. So a high power density. In a small volume, you can convert a lot of fuel. However, it results also in flame stabilization problems. Keeping the flame where it's supposed to be, that becomes the trick. We will look a lot at mixtures with 40% hydrogen, and you see that that already enhances the flame speed, but it's not linear. So 50% will be about here, and then there's suddenly a big jump. So above this percentage, the combustion properties really start to change. Although 40% is already showing a lot of different behavior. Yeah, this is also a classical slide, but I think it's good to show you anyway. There are always many ways how you can burn fuels, and there are typical two modes of combustion, and are non-premixed and premixed combustion. And non-premixed flames, the fuel and oxidizer enter separately, as you probably all are aware of. And what then happens is that, you know, you have to mix the fuel and air, and this mixing is rate determining because the chemistry is extremely fast. And you get a flame front where the stoichiometric ratio occurs, high temperatures happen over there, so we get high temperatures and therefore also high NOx formation rates. So typically this process is a bit slow because it's mixing controlled, and it's also very hot, and therefore we have long residence times, high temperatures, lots of NOx. So very often what we see nowadays are premixed systems. And premixed systems, you can mix the fuel and oxidizer. Therefore, you can get conditions where the ratio is lean. So we have an excess of air. So we are on the fuel lean side, where the temperatures are much lower than stoichiometric conditions. So you can prevent NOx formation in that way. However, we have an explosive mixture. Fuel and air are already mixed on a molecular level, so they can start reacting right away. And therefore, you get a sort of reaction wave that has a flame speed, and keeping this flame front at the location where you want it, at this location and not somewhere up here, which would be flashback, or somewhere down there, which would be blow off. To keep the flame over there, that's the trick in lean premixed combustion. Flame stability. Okay, so we need to know information about this burning velocity and how it is different for hydrogen, or how it depends on these properties that I showed you before. So it's time for some theory. Yeah, I would not say this is flame stretch theory for dummies, but I try to make it as simple as possible, keeping the essential things in there. If you want to know more details, I can refer you to the book of law, Combustion Physics, a very good piece of material, or to our own paper where we give a little bit more details, and specifically for the work I'm going to show you in a minute. So it's about the impact of the Lewis number on flame speed. We saw this high diffusivity of hydrogen. So how does that affect flame speed? Because flame speed is important for flame stabilization. Let's see. Well, let's start simple. Remixed laminar flames, right? They are reaction waves. Reaction waves that separate unburned gas from burned gas. And the unburned gas, you typically know the composition. The burned gas, well, when it's adiabatic, you can calculate what that condition is. I will only consider deflagration, so constant pressure problems here, no detonations, because that's usually not happening in most combustion equipment. So let's focus on constant pressure problems. However, these states do not tell us too much about how fast this flame front propagates, and that's actually what we want to know, the flame speed. And in order to say something about that, we have to analyze its internal structure. And we have to realize that this is actually a reaction diffusion structure. So we have reactions and diffusion happening. Diffusion of species, of course, fuel and air, oxidizer, but also conduction of heat. What is characteristic for combustion or for flames is that the kinetics has typically a very high activation energy. So that means that the reaction rates go faster and faster when the temperature is increased. And this is a sort of accelerating process, right? So combustion releases heat, so the reactions release heat, results in higher temperature, faster reactions, and so on and so on. So that means that typically you get an accelerating process with very high reaction near high temperature, and then suddenly it stops because fuel is gone, if you are in a lean condition. Yeah, I will talk about lean conditions mostly. So we get a sort of behavior over here, so where chemical heat release is shown as a function of a sort of reaction progress. The reaction progress is defined on the temperature from unburned to burned. And you see that the activity is mostly near the burn site, very closely to the burn site. In the limit, you can actually assume that this reaction zone, the chemistry in there, the burning rates, the chemical reaction rates are determined by the burn state, by the flame temperature, TB. Yeah, so it's not so much how hot it is here, it is how hot it is here that affects your reaction zone, the burning rate over there. And because of this high, well, small peak, of course, we get two zones here, thin reaction zone and a zone which is almost inert, where hardly any reactions take place. Preheat zone and a reaction zone. And this is very typical for hydrocarbons. Now let's make it a little bit more mathematical. A good lecture should contain lots of equations. Here are the simplest version I could think of for a 1D system. And now we are looking into a coordinate system that moves with the flame. So my gas is flowing into the system. Then I can consider a steady, most steady, pure one-dimensional system. Mass conservation is shown over here. Density times velocity. And that's continuity equation, basically. Here we have a conservation equation for the species mass, and here for temperature and species mass. I only have to look at the species mass because it's a one-step chemistry model that I apply here to keep things simple. One-step chemistry. Here's my consumption rate and I produce heat. Well, I can solve this. Yes, I can. It's not that hard if you assume that everything here is constant. This equation, of course, solving that means that the mass flow will be constant. This mass flux, rho times u, will be constant along the flame coordinate. And then using that in here, give you very simple solutions for the preheat zone, and my chemical source term I assume to be infinitely thin. Everything happens instantaneously over here at x is 0, the location of my flame front. So I get these exponential profiles for temperature and for the fuel mass fraction. With a typical thickness delta F, the flame thickness, thermal flame thickness, given by this expression. And well, here I show the example for Lewis number 1 fuel, because the Lewis number appears over here, and the Lewis number is the ratio between the mass diffusivity and the heat conductivity. So the mass diffusivity of the fuel. And if it's 1, then both these profiles have about the same thickness. Yeah, as shown over here. Good. So now let's look at mass burning rates or flame speeds. So how much mass can we burn? Well, you can do something that's called integral analysis. So you integrate the governing equations over the flame front from unburned to burnt. So from here all the way to there. Well, looking at these equations, if you integrate that from unburned to burnt, what you get, mass conservation, obviously. So what flows in is what flows out. And that is a constant, which we will call MB naught, where this naught, this 0 over here indicates that we are looking at a stretchless case. Later, we're going to consider stretched flames. Well, this is the fuel conservation equation. If we integrate that and we integrate from unburned to burnt, then this diffusion fluxes drop out. And what we finally get is this equation, because also the mass fraction of the fuel at the burn site is 0. All the fuel is gone. So we have these two expressions, which we can combine into one. And that says that the amount of mass flux through the flame front is equal to the amount of mass that we can consume in the reaction layer divided by the fraction of fuel coming in. Yeah, so what does this mean? That the reaction zone can consume a certain amount of fuel, and that fuel flows in over here, and of course the total mass is conserved, so total mass will also flow out at the back. And this mass flow, this mass burning rate for an unstretched flame is therefore equal to the mass consumption rate, the kinetics. Now let's consider stretched flames. First, what is flame stretch? Well, flame stretch classically is defined as the rate of change of a flame element or the surface of a small flame element. So I have my flame and I have two examples here. This is my flame, the blue thing in a straining flow. And I can consider a little flame element here, a surface element, because this is an infinitely flame front. And by the flow here, it will be strained, it will be stretched. So it will, this area will increase if you would consider it in time. And that is flame stretch. Well, flame stretch can also be caused by flame curvature. So this is another example where we have a uniform flow, but a curved flame. Also here you can consider a little element, a surface element. And because the tangential components of the velocity along the flame front here are in opposite direction, again, this little curved flame will be stretched. There's a third mechanism, that's flame motion. So but I couldn't draw that. If you have a spherical flame, it grows, it is also getting bigger. The surface is getting bigger, so it's stretched. So that's flame stretch. You can also define it on a mass basis by looking at a flame volume. This is a flame surface, but we have seen that a flame actually has a thickness. It's not infinitely thin. So if you consider the finite thickness, you can look at the mass in a little flame volume. So that moves with the flame, the mass in there, that can change because of all these phenomena, flow phenomena or curvature phenomena. And that's then a mass-based stretch. So in with that definition, which was introduced by Philip de Goeje, Jan ten Tye Boomkamp, you can define a stretch rate not only at the surface, flame surface, but also in the whole flame structure, also in the preheat zone. And basically what you get is that this is a mass loss term. So let's look at our simple strained flame configuration, planar flame. So I do not look at curved flames now, just to keep it simple. Strained flame, and then the stretch rate is the tangential, the divergence of the tangential components. So this in the direction of the flame, along the flame. But also over here, not only there, everywhere. So I get a mass loss term in my continuity equation. Actually, it's dV dy. And if I look at the continuity equation, I plug that in, I get this expression. Yeah, so mass is coming in, but because of stretch, mass is flowing out in the direction tangential to the flame front. Of course, this mass loss term is also present in the conservation for species. For my fuel, I have a similar term, which takes away fuel in this direction, planar, tangential to the flame front. Okay, so that makes it a little bit different, my equations. If I now perform this integral analysis, I get very similar results. Again, MB minus MU. But now they are different. It's not conserved anymore. So the mass flux, the burn side is not the same as the unburned side. In case of positive stretch, as shown over here, this is positive stretch. Obviously, you can also have the opposite. But for positive stretch, MB will be lower than MU. So the mass flux at the burn side is lower than at the unburned side. We can also integrate the fuel conservation equation. And we get this expression. Again, the burn side drops out because mass fraction at the burn side is 0. I integrate my source term and I integrate the stretch term. And remember that this integral over the source term is the mass burning rate of a stretchless flame. So the amount of fuel that can be consumed here is still the same. My chemical reactions still happen at the same rate. So I still can burn a certain amount of fuel. Well, if I combine this, basically substitute this in here, then I get an expression. I can derive an expression for MB. Write it as MB is MB naught. my stretchless burning rate, minus this integral. Here's my stretch, and here is the profile of the fuel. So for positive K, and this thing is always smaller than 1, so this must be positive. So for positive stretch, MB is lower than MB naught. My burning flux of my stretched flame is lower than the burning rate of an unstretched flame. Physically, what happens if you can burn here a certain amount of fuel, 2 kilograms, you lose 1 here, you have 3 kilograms over there of fuel that you have to move in per second per square area of flame front. If my mass fraction on the unburned side is say 10%, then I need 10 times more of total flux. That's 30 kilograms per second. But what I lose here is relatively more of total mass than fuel. That's this factor compared to this. So here I might lose, say, 15 kilograms, and then I only leave 15 kilograms of flux over here, which is less than the 20 I would have had if it would be unstretched. Yeah, so that's, you lose more total mass than you lose fuel. And that's why the mass burning rate of a stretched flame is lower than the unstretched flame. With this term, and that's the Karlovitz integral. So you integrate the Karlovitz, the stretch profile over the whole flame structure. And that gives you a sort of mass loss, and you normalize it by the mass flux of the stretchless flame. That gives you then a dimensional stretch rate, a Karlovitz integral. I cannot see what happens on the right edge of my slides. It's a bit nasty. I can also not point over there, but that should be something like a Marx-T number and a Karlovitz number over there. Well, not Marx-T number, not right now. We're gonna do that soon. But because that, I did not consider that. I did not talk about Lewis numbers. I did not talk about diffusivity. That comes now. Because where does the unity Lewis number or the non-unity Lewis number effects come in? Then we have to consider enthalpy. Look at the enthalpy. So that's the sum of fuel and temperature. That's chemical heat and sensible heat, let's say. If we plot that for the unity Lewis number case, it looks like this. We can add those two up. And if you normalize this all conveniently, and I added a little separation over here, you get a constant. It's purely constant in the unit Lewis number case. And the burned side equals the unburned side, of course. However, for non-unity Lewis number cases, this profile changes. Fuel profile, lower Lewis number. Let's say for hydrogen it's 0.3, so we get a much wider profile here. It diffuses much more, so we get a bigger thickness over there. If we then add these two up, you get a dip here. Yeah, there's already fuel disappearing, but the temperature is not rising yet, so that means the enthalpy is going down locally. However, at the end it will be constant. It's of course conserved. Doesn't change. Now add stretch to the picture. This was still unstretched. Now let's add stretch. What then happens? If we do the integration again from unburned to burned, we can get this relation. So we lose some enthalpy looking at this, but of course mass changes as well. So we have to combine this with the continuity equation. Then we get an expression for the difference between the enthalpy at the burned and at the unburned side. So my energy content of the mixture changes with this profile. Well, since the enthalpy is lower than the unburned enthalpy, and if I have positive stretch, that means this is negative, but here is also a negative. So HB will become higher. So for a flame with a Lewis number smaller than 1 and positive stretch, the enthalpy at the burned side of a flame will be higher than it was at the unburned side, which was equal to the stretchless case. And an increased enthalpy, of course, means an increased temperature. which I didn't draw here, but this increase would also result in a higher temperature, flame temperature, and higher flame temperature means directly that this source term here, where the reactions occur, feel higher temperature, so we get higher reaction rates. Higher reaction rates means higher consumption rate, higher MB0, higher consumption rate. So this story not only applies to the enthalpy. In general, we have many species and they all have different Lewis numbers, typically not one. And therefore also the elements are not conserved. So the amount of carbon or hydrogen or oxygen in the flame, which are conserved by chemical reactions, would be uniform, constant. But when stretch and non-unity Lewis numbers are there, also they can change. The element mass fractions, Zj, will change at the burn site. And that has also an effect on the chemical composition at the burn side of the flame. The flame temperature will change. If you get more hydrogen, more fuel, more water, that has an effect on the chemical equilibrium temperature, the composition, which directly determines the reaction rate over there, right? The reaction rate was determined by the burnt side of the flame. So the mass consumption rate or the mass burning rate of a stretchless flame, which are equal, is a function of this burnt composition in terms of enthalpy and elements that determines the equilibrium composition, the burn side. So this stretchless depends on the composition of the stretched case. So if you plug that into the mass burning rate, so this is the same expression as before, but now we're clearly expressing that this MB0, the consumption rate, the chemical activity of the reaction layer, depends on the composition at the burn site. Still, there is this Karlovich effect, of course. If we linearize this around the stretchless composition of the burn site, we can derive an expression like this. So now MB0 is again MB0 at the stretchless conditions. We get this expression, 1 minus Karlovich, and this is what we call the direct stretch effect, which I explained first. And then here are additional terms which express the effect of the change in enthalpy and elements on the consumption rate, MB0. So I can get a higher enthalpy at the burn site that results in a higher consumption speed, and that's added to the mass burning rate. So you can burn faster. And here we have our Mach-T number then. Yeah, so this was 1 without preferential diffusion for the unity Lewis number case. But when you don't have, when you have non-unity Lewis numbers, this Mach-T number can change. That are given by these values. So let's see how this works in practice. Look at a counterflow flame, stretched premixed counterflow flame, methane air. These are calculations, by the way. We have here lots of measurements, those calculations, but for different strain rates, low strain rate, high strain rate, and the theory nicely captures this. So it seems to work. The weak stretch theory, that's linearization, is a bit less for the relatively high strain rates. Notice that at this strain rate, the flame quenches, but here it looks very nice. Okay, this is for methane, unity Lewis number, slope -1. Now we're going to add hydrogen. This is the pure methane case again. Now with Lewis numbers not equal to 1, and we're going to add hydrogen, hydrogen, more hydrogen, more hydrogen, because preferential diffusion results in a change in elements, and that results in an increase in the flame speed. This is for lean methane hydrogen mixtures in air. What are these changes then? Well, here are the changes shown for this case, the 60% hydrogen. So we have here the enthalpy, which is going down, oxygen is going down a little bit. This is not only the change, but also weighted with their effect on the mass burning rate. So this is the direct contribution in the MB0. But the biggest contribution comes from hydrogen, the element hydrogen. So actually the increase in the hydrogen content at the burn site, and I'm talking about the element hydrogen because H2 is not there anymore at the burn site. It's the element hydrogen results in an increase in reactivity, typically because this results in a richer burnt composition, which has a higher flame temperature. Higher reactivity at the burn site, higher mass burning rate, higher flame speed. And we see that now the flame speed is not decreasing anymore, but actually can even increase. And this is an interesting phenomenon. We see that here, again, this is the Mach-T number. So typically it's positive, meaning that the slope is going down, but that significantly amounts of hydrogen, and that happens for lean flames earlier than for stoichiometric flames, but at a certain hydrogen fraction, the Mach-T number becomes negative, meaning that this mass burning rate goes up with stretch and not down anymore. And you say, who cares? Well, I do, and many flames do, because this stretch phenomena is very important for the stabilization of flames. When this Mach-T number becomes well, negative, actually what you then see is that you get lots of instabilities in flame fronts. Here you see experiments, pictures of experiments showing cellular flames. Why is that happening? Well, in fact, all flames that have a density jump are hydrodynamically unstable because, and well, it's not so easy to explain, but consider if you have a flat flame and you now perturb it a little bit, put a little wave on top of that in shape, what you get is that you get an expansion of the flow in front of the flame because of the acceleration here. The density jump causes an acceleration normal to the flame, and therefore you get a little expansion of a flow tube in front of the flame. So the velocity will decrease because of this expansion towards the flame front. The velocity will here be lower than the flame speed. Hey, velocity lower, then my flame will start to move faster. So this bulge here will grow and grow and becomes unstable. However, this part of the flame is also stretched. It's positively stretched, right? We remember that, flow in this direction, velocity. So this little part is also stretched when it grows, and positive stretch results in lower mass burning rate. So my SL goes down, so it can stabilize again. And that's why methane flames look flat. And this here is a methane hydrogen mixture, which shows a lot of bulbs. Because when I add hydrogen, my mass burning rate with stretch goes up. Actually, this flame speed can even increase when it's positively stretched. So this can be intensified. And the opposite holds here, of course, this goes back in that direction. So my wrinkles grow and grow for cases with very low Lewis numbers for hydrogen. And I get lots of these finger-like structures, little islands. Hydrogen flames like to be stretched. When they are stretched, they burn stronger. So you see a lot of cusps being formed because there they burn more intensely. And this has a bigger impact on flame stabilization. Well, let's look at flame stabilizing on burners like this, where we have a metal plate with holes, very simple system. And typically you have stabilization when the gas velocity equals the burning velocity, right? So if I blow in harder, my flames will adjust, they will get bigger to get a balance between gas velocity and flame speed. That determines stabilization. Yeah, when these two are equal, then a flame can stabilize. Well, you may say, if I look closely at this hole, at the wall of this hole, the gas velocity is 0. So the flame speed is always higher than the gas velocity, so it will flash back always. Well, that's not the case because the flame cannot burn very close to the wall. It loses heat and you get a little close gap extinction locally. This is typically the size of a flame thickness. So in order for this to propagate in there, the velocity at one flame thickness away from the wall is relevant. So the gradient of this velocity is relevant. And that's the critical gradient theory of Lewis and von Elmer. So at a certain low distance from the wall, typically a flame thickness, the velocity is important, this gas velocity. How does it compare to the burning velocity? If the burning velocity is higher, it will flash back. So we did some experiments with methane hydrogen mixtures, and it's mostly done by Yuri Soshin, this work. We compared mixtures which have the same flame speed, so same flame speed, then for the same gas velocity, you would expect similar flame shapes. And with increasing velocity, of course, the flames get bigger. Well, that nicely works for a methane flame here, a lean methane flame. A methane flame with hydrogen added to it, 40% hydrogen, shows also this increasing trend, but the shapes are different. You can clearly see that there's more intense burning here at the lower edge of the flame, where the flame is positively stretched. Here on the tip of the flame with hydrogen, it's negatively stretched, it's compressed actually. You have a curved flame in a flow like this, so it's compressed. So you get weaker burning in the flame tips and stronger at the foot of the flame, the base of the flame, and that results in that changes the stabilization. It burns stronger at the foot. So to study this in more detail, we did a lot of experiments and numerical simulations on this configuration, a cylindrical bluff body, to study the flame stabilized on top of that. And we looked at different inlet velocities and different mixtures, equivalence ratios. At what conditions can we find a stable flame, and at what conditions will it blow off or flash back? Well, mainly blow off was studied here. So let's look at some results. Here we see experimental results and numerical results in very good agreement. And if you add the same burning velocity, so you expect the same shape, but for the hydrogen added, you see it burns more intensely to the bottom, at the bottom, and that gives a somewhat wider flame. Well, simulations showed similar behavior, and it gives a very, gives us the opportunity to do a very detailed analysis of heat loss, flame stretch effects, and preferential diffusion in here. Would be too much to go into detail now, but you can read the paper which is published recently online on all these phenomena that play a role. So you have heat transfer to the body. Interesting phenomena is that this heat is then recirculated, but also this hot body attracts hydrogen. Hydrogen is sensitive to thermal diffusion. If this is hot, hydrogen diffuses towards the hot side. So you get a slightly richer condition over here, more hydrogen over here, which helps in stabilizing this flame, or maybe even makes it burn too strongly, and then you get flashback. But let's look at blow off. So what did we do? Look at the limits. So yeah, take a existing inlet fixed velocity, inlet velocity of 1 meter per second, then you make the mixture leaner and leaner and leaner. At some point, the flame will blow off. Well, here you see the flames were did not blow off, the lean limit flames. Well, propane looks like this. It has a Lewis number much larger than 1. Methane, Lewis number about 1. And here we go below 1. And the lean limit flames look very different. You get this like sort of pencil-like flames. And when they quench here. While normal propane methane flames, what happens? They just move upwards. They blow away. Here they quench. And what can happen even is that this flame over here stays alive. Let's look at that. So for a condition with a pure hydrogen, and that just we saw 40%, this is 100% hydrogen at 1 meter per second. And then we, well, this is already lean, but we can go leaner and leaner and leaner. And then you get this needle, but more intense burning over here, strong stretched. There's also a recirculation zone over here, where this flame likes to stay inside. Then it quenches this part. You have a tubular flame at some flow rate. When you get even leaner, that part quenches. But we can get a residual flame, we call that, and even at the end, a very nice spherical flame, which is steady, remains there for minutes, as long as we want, basically. If we can keep the flow very nice and steady, it stays over there. Very lean conditions. If you would go back, it would reignite again, probably. So it also has technical consequences. We did also some simulations of this and found very similar shapes. Also, well, for the richer conditions, it was perfect agreement. For the leaner conditions, it gets a bit worse, but you can still see the residual flame and almost a flame ball. Unfortunately, in our simulations, it quenched after some time because of heat losses. But in general, very good agreement. An interesting phenomenon. So these flames can burn in extremely lean conditions. But there's something more interesting probably. So if you look at different velocities, you do this experiment at different velocities, you would expect that at a higher velocity, the lean limit is higher because you need a higher burning velocity. But for hydrogen, it's the opposite. If you do this experiment at 20 or at 40 centimeters per second, at 40 centimeters per second, you can go leaner. That's because at 40 centimeters per second, the stretch rates are higher, and this lean flame likes to burn at high stretch. It begins to burn more intense. So you get what we call anomalous blow-off behavior. It's directly opposite to methane or other natural gas, propane, etc. Other hydrocarbons show the same behavior. Very striking observation, and it was also seen in simulations, by the way. Well, other side is the flashback, of course, flames flashing back. This was blow off. Now look at flashback. We did simulations of hydrogen, pure hydrogen flame on a slot burner like this. So 2D detailed chemistry, all the fancy work, whatever we can do. And then you lower the velocity, and at some point, of course, the flame flashes back. We see here the temperature for a lean 0.7 case. So this is how we then measure the flashback limit. If we do this for different conditions, so from stoichiometric to lean, we find at the limit similar shapes. However, it's clear that for the very lean case, there's a very strong preferential diffusion effect. It starts to burn much stronger near the base, actually about 3 times stronger than the stretchless case. So a flat stretchless hydrogen flame for this condition would have a heat release rate that is 3 times lower than this. So if you would use this theory between gas velocity and flame speed, you would find similar flashback limits for all, but here this preferential diffusion makes the flame flashback at way earlier, at way higher velocities, because it's burning much more intensely there. So if you want to derive expressions for that, you have to include that. You have to include this preferential diffusion effect in the flame speed, and we recently did that, and that's now submitted to Combustion and Flame. Well, most of these simulations we did so far were steady, but we also tried some unsteady simulations, and then you see some interesting phenomena, actually. This is a slightly wider channel, and what we did here is lower the velocity in a step, and I'm not sure if I can play this again, but what you first see is this nice dancing flame, and then it's not deciding which side will flash back first, and then boop, it goes down. In fact, it stabilizes over here. So it's maybe more complex than what we think, and a good detailed experimental campaign comparing that with numerics might be needed. Most of this experimental studies are dating back from the 80s. Okay, what's a presentation by Jeroen van Oijen? Not about FGM. Well, I have 7 minutes or so to talk about FGM. Let's do that then in a very quick way. FGM, of course, is a method for simplifying chemistry. Hydrogen chemistry is already simple, you would say, but still, if you would do these kind of 2D simulations, they take about a couple of days. And if we do hydrogen simulations with detailed chemistry in a full boiler configuration, it's weeks, even longer. So simplified chemistry is still needed. And FGM is one of those methods. And in FGM, what we do is we calculate 1D flamelets, store those in a table. We call that mathematically is the manifold, basically saying that the chemical composition in a flame can be parameterized by one variable, the control variable. So we compute a premixed stretchless flame where we have a progress variable, which is typically a product of water or CO2. And here is the source term of that species. We tabulate that as a function of the progress variable. And then we can use that in the CFD code, the source term as function of a progress variable, and solve this equation in the CFD code and look up the source terms. Okay, this works very nicely. We've applied that to many cases, methane, lots of different fuels. Often, however, we also have to account for effects that are not present in the 1D flame, and that are effects like heat loss or variations in the equivalence ratio, in the stratification, in the technical application. Then you have to add these dimensions to the table. So if you have heat loss, you have to add enthalpy as an additional dimension. So you solve flamelets for different enthalpy. You store that in the lookup table as two of these coordinates, so the progress variable and the enthalpy now is an additional coordinate control variable. And you get a lookup table that looks a bit like this. So here's my source term of the progress variable, and I can couple it in the same way and solve equations for these two control variables in my CFD code and look up the source terms in this table. Okay, that's the simple explanation. Now, if we want to apply this to hydrogen, what should we do? Account for these variations that hydrogen causes. Hydrogen also causes variations in enthalpy in elements. These are the preferential diffusion effects. So we should include that in the table. 1D flamelets do not have that, the 1D manifold, I mean. So we have to add that to it. And you can do that in different ways. But the good thing is that for weak stretch, at least, you can show that these variations are linearly coupled. They all are linear in Karlovitz number, so they are also linear coupled. And you can therefore combine all these variations into one dimension. You only need one parameter to describe this behavior. Well, in practice, what we do, solve stretched equation, flamelets, both positively and negatively stretched flamelets, because in practice, also positive and negative stretch is observed in flames. So you solve flamelets for stretch, you get again, well, you can then transform that in a 2D lookup table, a 2D manifold, and here is one shown such a manifold. What we see here is the source term of the progress variable as function of the progress variable, and the second parameter, which is an element mass fraction. Actually, it's a linear combination of carbon and hydrogen in this case, just to get a nice mapping of this space on the control variables. We see here the stretchless flamelet, and we also see a stretch, positively stretched flame. And what we see, as expected for this methane hydrogen mixture, what it actually is, that a positively stretched flame has a higher carbon and hydrogen content and enters a region where it burns more strongly, as explained before. Yeah, so we have to include these terms also in the transport equations, and I will go quickly through this in view of time. So we have to model that term over there, and we can do it in different ways. And we recently introduced a new one, which is very suitable for hydrogen flames, because it also includes transport tangential to the flame front. Well, that's explained in this paper recently published online in CTM. So I can recommend reading that. So we can test this in stretched flames, again, like we did before. And here you see the detailed simulations, the mass burning rate going up for Karlovitz numbers, positive. With a 1D manifold, there are no stretch preferential diffusion effects, so we only get the direct effect, and that means mass burning rate goes down. But with preferential diffusion in a 2D manifold, we can nicely capture this. So burning velocity increases, and the exact details on how it is created, this 2D manifold is not that sensitive. As long as the variations in element mass fractions and enthalpy are there in the right way. So we apply this also in DNS of this mixture, 40% hydrogen, lean case in spherically expanding flames, well, actually cylindrically, because it's 2D, detailed chemistry simulations are pretty expensive. So 2D is already hard. And if you then do that with an FGM, 1D, you miss this preferential diffusion effect. If you do that with a 2D manifold, you do capture these phenomena. You get the intense burning in the flingers that are formed. And maybe the biggest gain here is that we get almost the same result, but then 200 times faster than here. That's why we do FGM, right? To make it faster. Here, these simulations were still strongly affected by the initial turbulence that is there. So I put a spherical flame in some turbulent field, and therefore these develop more or less all the same. But if you want to gather some statistics, you have to run longer. And that's why we did this case, a Bunsen type flame, a DNS of simulation with FGM. Here, the premixture comes in the slot burner, and there's burnt gas coming along, and you get this kind of simulation. And you all have seen this simulation because you have visited the website of the Dutch section of the Combustion Institute, and it has this movie on this intro page. Well, we did this case, 40% hydrogen, and we did this with one-dimensional FGM, so it does not predict Lewis number effects, and with a 2D FGM, and it has the Lewis number effect. So it can predict preferential diffusion, and it can predict intense burning in regions that are convex towards the unburned side. So you get increased burning rate here. And what does that mean? That this thing here, this little flame front area grows and creates more and more flame surface. And that means a higher flame surface density in this area, means a higher burning rate, turbulent burning rate. In fact, what we found is that turbulent flame speed increases by 30% for this mixture. That's significant. And of course, we have to include that in our modeling or in our analysis of these flames. Well, it's an unsteady phenomena, preferential diffusion, so it takes some time to set in, about 1 flame time scale, and that means that very fast fluctuations in stretch, positive, negative, positive, negative, positive, negative, might be damped out. So very high fluctuating flows may have a damped effect. And modeling this is a challenge because, well, in DNS, we can all resolve that, and we can capture this phenomena, but in an LES or in a RANS, this is all happening on the subgrid scale or on the unresolved scales, and you have to model it. You have to think about a model. Well, that's a work in progress. Many people are looking into this, and we are trying to run DNSs of highly turbulent flows to study these phenomena and then to come up with models that can be applied on a larger scale, LES, for instance. Well, final slide. I'm running a little bit out of time, but I hope you can still stay with me. Some other modeling challenges. So that's one big challenge, but other modeling challenges are, well, I started the whole story by saying that flames are thin, that we have high activation temperature and a preheat zone which is rather inactive. And for hydrogen flames, that's not the case. Hydrogen flames, if you look at the heat release rate versus progress variable, hydrogen burns everywhere. It has a hydrogen production, hydrogen radical production layer at the high temperature side. That's the same as in hydrocarbon flames. But the hydrogen radicals diffuse upstream, and there they react with the oxygen. And that reaction can actually happen almost at room temperature. And it's an exothermic reaction, highly exothermic. So you get a lot of heat being released at the leading edge of the flame, very close to the unburned side. And that's, well, results in flames not being thin. So the whole theory should be reconsidered maybe, or extended to account for this. For FGM, it also causes some problems because, well, high burning rates close to zero progress variable means that your flame gets very sensitive to little perturbations here. But there's something else. The source term over here depends strongly on what happens a little bit further downstream. Because the hydrogen radicals produced here diffuse upstream and cause a lot of reactivity over there. So it's not local anymore. And therefore, when a flame is cooled at the burn site, there's no radical being produced, there's no activity over there. But in a flamelet where I have a constant enthalpy level, there will always be activity. And this results in an overprediction of the burning of the source terms here in the leading edge, and that may result in way too high flame speeds and a very early flashback if you would study flashback on these burner flames like we did before. So we have to solve this. Actually, we have already ideas on how to do that, but that's for the next presentation. I want to thank you for your patience. This is basically a summary. Highly diffusive hydrogen. Therefore, we get very strong preferential diffusion effects, right? Hydrogen flames burn stronger when stretched. They like to be curved and stretched. Results in cellular instabilities, increased flame surface density, anomalous blow-off behavior, and very prone to flashback. That's in a nutshell what I've been trying to explain to you. Again, thank you for your patience. I want to thank all my sponsors, of course, and all my colleagues at TUE who participated in this research. Thank you all.